Welcome back to the course of chemical crystallography in the second week. Today we are going to start learning how to draw the 2D space lattices with symmetry elements incorporated in it. So today what we plan to do is that we will try to draw and show you how to draw these 2D space lattices having different symmetry elements. So in case of 2D lattices, the first 2D lattice that we can draw is termed as P1. So this is a lowercase p. You remember that lowercase p here indicates a primitive lattice and 1 indicates there is no other symmetry other than translational symmetry. So we do not have any other symmetry. Only translation. So in this case, if we draw the 2D lattice like this, which is actually a combination of 4 unit cells, if I start writing one object, my molecule, as P, I have chosen the letter P because this letter does not have any symmetry of its own. So when we apply any further symmetry operations, it will not hamper the molecule at all. So when I say P1, I should have this P translated in all the 4 unit cells like that. The second type of 2D lattice has a space group small p2, which indicates it has a twofold axis of rotation. This twofold axis of rotation is important to generate the symmetry related objects around it. So I am again drawing 4 unit cells like this, and then I have my object P here, and the symmetry element that we have here is twofold axis. So I am putting this twofold axis at every corner of the lattice of the unit cell. And then the first important symmetry is a translational symmetry. So I should have the molecules translated like that, and then based on this twofold axis, if I rotate this, the first P that we have here, which is this particular P, if I rotate it should come outside the unit cell, and we should draw it like this, which looks like D. In the same manner, other P's also can be symmetry operated, and the corresponding translation related molecules can also be drawn. So now what we see is that the symmetry between this particular molecule and the other molecule which is there, they are further related by a twofold symmetry. Similarly, these two are further related by another twofold symmetry, and there is a further twofold at the center of the unit cell. Similarly, there is a new twofold generated at the middle of the edge, center of the edge, and so on. So because of the presence of twofold axis at 4 corners, what we have got are twofolds generated at the edge centers and the center of the unit cell as well. The next type of 2D lattice is termed as PM. Once again, P is small and M means a mirror plane. So we have only one mirror present in the lattice. So now if I draw again a 2D space lattice, and then I write the letter P, which is my object, and it is translational symmetry related objects are also drawn in the adjacent unit cells. Now when I am saying that it has mirror symmetry, I must designate where the mirror is. The mirror, as I said, is designated as a bold line, and I am assuming that mirror is along this edge. This edge represents a mirror. Similarly, this edge represents a mirror, that edge represents a mirror. So these blue lines are mirrors that are present in this lattice. So what happens when we apply this mirror to the object that I have taken? I get mirror image related objects like this. The translation comes here, the mirror comes there. So now P becomes B by a mirror operation. So now what we see is that a further mirror is generated through the middle of this unit cell as I am drawing those lines. So these are additional mirrors that got generated between the two parallel mirrors. So in this particular case, in one unit cell there are two molecules which are mirror related. In case of the previous lattice, which is P2, there also, if you see, in one unit cell there are two objects, two molecules related by a two-fold symmetry. So in case of P1 you have one molecule per unit cell. In case of P2 and PM you have two molecules per unit cell. Now let us see the fourth type of lattice in this two-dimensional space lattices is number 4 is PMM. That means it has two mirrors perpendicular to each other. So how does it going to look like? Once again, we first need to draw the combination of 4 lattices, 4 unit cells rather. I am going to draw only the translation related objects as usual. Now we have one set of mirror as before along one particular edge. So if I apply that mirror like before, we should generate the objects as I am drawing here. And then the second set of mirrors that are there or that one can consider is a transverse mirror like this, which is perpendicular to the previous mirror. So this is longitudinal mirror and the new one is a transverse mirror. So now we see what is happening. Now we try to reflect the objects that are here P and B against the mirror transverse. Now we get these objects which are now mirror image of the previous one. one can complete all these by drawing the corresponding mirror images. So now what has happened, if you look at this particular drawing very carefully, first of all, because of parallel MLs that we have here, we have generated one additional longitudinal mirror here through the middle of the unit cell, and one transverse mirror through the middle of the unit cell as well, perpendicular to that. So this diagram completes the PMM. Now I would like you to see one more interesting aspect here. Wherever I have a point of intersection of two mirrors, at those points I have a twofold generated. So wherever two mirrors are intersecting, a new twofold has been generated. So overall, this PMM lattice or PMM space group contains two perpendicular mirrors, ML and MT, and wherever those ML and MT coincide or they cross each other, the point of intersection is a twofold axis that is generated in this case. Now we go to some more slightly complicated two-dimensional space groups, and mind you, it will not be possible for me to draw all of these in this class, but I would like you to see these drawings and understand yourself from a textbook by F.A. Cotton, The Chemical Applications of Group Theory, chapter 11. All these drawings have been done there, but some of those things which I felt is required to discuss in the class, I am trying to draw them as much as possible. So the next one is P3. So which means I have a threefold symmetry present at the corners. As you know, we draw threefold as a triangle. So I am drawing those threefold axes at the corners of the unit cell, and then I am writing the letter P here, and then when we try to apply a threefold symmetry on this P, this gets rotated like that. So by applying that P, if we try to fill the unit cell, what happens is that in between the threefold axis, the three-corner threefold axis, these three threefold axes are further related by a new threefold, and similarly the other three threefold axes are related by another threefold axis. So P3 looks like this, as I have drawn, with threefold axis present at four corners and two opposite centers of the half triangular portion of this oblique lattice. Now let us try to draw another one, which is PG. I am only going to do the ones which may be difficult to understand. The rest of it I would like you to go through the textbook and do it yourself. As I said, it is glide. So the glide symmetry is drawn as dashed lines. So the unit cell is drawn with bold line, but the glide is drawn as a dashed line. So now if I have my object which is here, what I am going to do is I am first going to draw the translation related objects. And then we will draw the objects which are related by the corresponding glide which is here. What is a glide plane? A glide plane means you do a reflection followed by translation. So if I was going to just reflect it, it would have appeared here. So that means it is just a mirror. But no, I don't want only a mirror, rather I want it to be translated as well. So when we do a reflection followed by half translation, the object comes here. Similarly, the object which is in the lower unit cell, do a glide plane, it comes somewhere there. For this, the atom comes there. For the fourth one, the atom comes here. And if I have this in the outer unit cell as well, the corresponding points come there. So now what we see is a relationship between the two objects inside the unit cell is also a glide in between. So this is the picture, this is the representation of the 2D space lattice PG. Now, as I indicated, there may be a lattice where you have a C-centering, a lattice centering, a centered lattice. So let us try to draw one of those centered lattices. When we write CM, it means it is a centered lattice plus it has a mirror. So first let us draw a simple centered lattice. A centered lattice means in addition to an atom at the corner, I should have another atom in the center of the face. So I should first draw the corresponding translation related objects in all the unit cells that we have drawn here. So these are just the corresponding translation related objects for a C-centered lattice or a C lattice. So now, as I said, there is a mirror plane and this mirror plane is a transverse mirror. So we take that mirror along the edge. This is my transverse mirror. And this transverse mirror is further present in the middle of the lattice, like this. So now with the transverse mirror, we try to apply the mirror symmetry on these points. So what I get is the object here, the object there, the object here, object there, and so on. In that process, what has happened is what we see here, the points identified here and point identified there, they are further related by a glide in between. So, if we try to draw this glide with a different color, the glide should come like this. So, in a nutshell, if we try to just draw this unit cell without drawing any object, it should be drawn like that. These are mirrors which we have. As I indicated, mirrors are drawn as bold lines, and the glide planes are drawn as dashed lines. This is the representation of CM with only symmetry elements indicated. The other one that I want to draw is a four-fold symmetry, which is P4. So now, as we see, it is a four-fold symmetry. The immediate requirement is that it should be a square lattice, not a rectangular lattice anymore, because A should be equal to B. So now I am going to draw a square lattice, rather a square unit cell, which is my P4, where I will draw the P4, and I am going to place my four-fold axis at four corners of this lattice. Now let us take the same object P and do a four-fold operation on P along those symmetry elements. So when you rotate this P anti-clockwise direction, you get something like that. On further rotation, it gives you this. On further rotation, it gives you that. And the same is present due to translation at all the four corners. So now as a result, you can see that a four-fold is generated at the center of this unit cell as well. The four P's inside the unit cell are related by a four-fold symmetry, and further there are two folds which got generated at the middle of the edges. So these are the symmetry operations that got generated because of the presence of four-fold axis at four corners and at the center. So all these drawings, all these two-dimensional space lattices are important to understand the growth of three-dimensional space lattices in the future classes. So I would like all of you to go through the textbook by F.A. Cotton, the chapter 11, and these drawings are taken from this particular journal, Journal of Chemical Education, 1985, volume 62, page number 35. It is required for all of us to draw these diagrams ourselves to make us understand that how these symmetry related objects are generating, because this is the most important aspect of X-ray crystallography, because we are trying to understand how one molecule is trying to see another molecule, and then when we are trying to see two different molecules in space, how they are oriented in space. Here I would like to give you a small demonstration where, suppose this is a remote control of AC which has two sides different. So now if I have one object here, I apply a mirror plane like this, the object is reflected here. So the digital side is always facing you. But then if I have a two-fold axis like this in space, this object, when it rotates like that, so the digital side is now towards me instead of towards you. So while drawing a mirror compared to a two-fold, there should be a distinction in our drawing. So if we are trying to draw some triangle and a mirror, it should show like this. If I am drawing a triangle and I do a two-fold, that also shows like that. The sign for two-fold is this, and sign for mirror is a bold line. But to distinguish between these two, what one should do is identify the face with a dot. Here the face is identified with this digital side facing towards you. So when I do a mirror plane, the digital side remains towards you, but when I do the same for a two-fold, it rotates and the side changes. So this change of side indicates, if I have a dot here, the dot goes behind. So in representation of three-dimensional symmetry, when you represent something which is not in front but in behind, we represent it as an open circle instead of a dot. So we will use these notations in future lectures so that we are able to represent three-dimensional objects, three-dimensional symmetry elements, three-dimensional symmetry operations as a projection in 2D, that is our pen and paper or blackboard or whatever. We should be careful about what we are drawing, whether we are drawing a mirror or we are drawing a two-fold, whether we are drawing a glide or we are drawing a 2-1, it should be distinguished appropriately. So today what we learned is how to draw the 2D space lattices with the objects. In the next class we will try to draw the same lattices without any object but by placing only the symmetry elements, and then we will learn a few new things like what is the difference between P3M1 and P31M. So with this I would conclude this lecture today, and we will discuss further in the next class.